So if you take a single muscle cell and you do this, and you give it incomplete tetanus, yeah, then you'll see this kind of jittery motion here. And so when your eye is fidgety or your arms are fidgety, that's a different phenomena where you're changing between motor units, and one motor unit is failing before you can swap to another motor unit. We'll talk more about that in the lab when we talk about EMGs. But yeah, if you're just observing one muscle cell, or you're innervating all the muscle cells, and at incomplete tetanus, yeah, then you see jitteriness. Sometimes you see jitteriness just because you're just exciting a lot. So, like caffeine is a stimulant, so you'll see like that too. Yeah.
My dad is kind of like, he has like shaky hands.
Yeah. There's a different reason why you have shaky hands. It could be muscle atrophy. It could be something about the nervous system. There's different reasons. Any other questions about muscles? No? Okay. Well, any review questions about any of the material, all the way from back from chapter 6 until now? You guys have no questions. You guys know everything? Yeah.
Back into the nervous system, I'm still having like some problems with the equation, like the Goldman.
Yeah. Alright, so the Goldman-Hodgkin-Katz equation?
Right.
Okay, well, let's first talk about the Nernst equation. Really, the Nernst equation was telling you, given charge of the molecule and the chemical gradient, it could tell you what the equilibrium potential is. That's what the Nernst equation was telling you. I don't care if you know that equation. I don't care if you can use it to calculate equilibrium potential. I just want you to be able to know this and this. Can you tell me if your equilibrium potential is positive or negative? I went over that in a review question a couple lectures ago, right? Like for example, chloride, given it's high on the, high on outside, low on inside, and it has a negative charge, that gets you a negative equilibrium potential. Like you should be able to think that through and why that's the case. So that's what the Nernst equation tells you. So the Hodgkin-Goldman-Katz equation basically tells you the same stuff. So given charge, given chemical gradient, and this is important, and the permeability, it will tell you the actual potential. So what it's taking into account is, so in the Nernst equation, it assumes there's complete permeability. Like, whatever ion you're looking at can freely pass into and out of the cell, given that other things cannot. So if you're looking at, let's say, potassium, all the sodium, all the chloride, all the proteins are staying where they are, but if potassium will freely move back and forth, you can expect an equilibrium potential of negative 90 millivolts. That's what Nernst equation is telling you. The HGK equation realizes, you know what, all these ions are moving, but they're permeable at different rates, right? Potassium is about 40 times more permeable than sodium, and it's about twice as permeable than chloride. And so they're going to have different effects on what the membrane potential is because they're moving in and out at different rates, right? That chemical gradient can be different. And so that's why they include this permeability factor. And so given all the permeability, given all the charge and the chemical gradient, you can calculate what the actual membrane potential is. And so that's how we get to the negative 70 millivolts, is through this equation. And so the trick is, if you change if this changes, you will get closer to the equilibrium potentials you see in the Nernst equation. So if you open up let's say you open up all the sodium channels, so it's completely permeable, the potential of the cell potential will move closer to the equilibrium potential of sodium. So this equation is also kind of giving you there's this tug of war between all the ions towards their equilibrium potentials, right? If potassium had its way, the cell membrane potential would match its equilibrium potential of -90. If sodium had its way, it would be positive 60. So this -70 value is kind of the compromise or the additive effect of all those ions together. And if you manipulate one, you are moving it either closer or further away to its equilibrium potential. Does that make sense?
Yeah, yeah. I mean, I would agree with you, but like it's more clear for sure.
Okay.
Yeah.
Yeah, it's something that's kind of hard to wrap your head around. As you saw from me, I had to backtrack to explain myself over again. Even I get confused every once in a while with this stuff. Any other questions? No? Okay, well, if there are no other questions, you guys are free to go. Thursday is the exam 2. Bring a Scantron, bring an ID, of course, and yeah, we'll take the whole period.